Buffon's needle. Part A. A table of infinite expanse has inscribed on it a set of parallel lines spaced 2a units apart. A needle of length 2l, smaller than 2a, is twirled and tossed on the table. What is the probability that when it comes to rest it crosses a line? Part B. Now assume both horizontal and vertical lines exist on the table. What is the mean number of lines the needle crosses? Part C. Now let the needle be of arbitrary length. Then what is the mean number of crosses? Let's start with the part A. This part involves some geometry, so let's draw a figure. Let these vertical blue lines represent the lines inscribed on the table, with 2a distance apart. And this horizontal dotted line is going to be a reference line for us. Next, let's assume that the needle, shown by this green line, lands at an angle theta to this reference. Each arm of the needle will have a length of L, and let's call the center point C. Overall, the vertical position of the needle doesn't matter in this problem, because the lines on the table are vertical. What matters is the horizontal positioning of the needle and the angle theta. Let's look at the edge cases where the needle almost crosses the vertical lines. That is represented by these two cases on the left and right. Let's call these side distances x. So note that the needle will not cross a line if its center C is outside of x, and it will cross if it's inside of x. That's why for a fixed theta, the probability that the needle crosses the lines, let's call that lambda sub theta, is 2x divided by 2a, which is x over a. That's because we are assuming that the center C can land anywhere in between the lines with a uniform distribution. Now, the above is for a fixed theta, but note that x is a function of theta. Namely, x sub theta is equal to L times cosine theta, as you can see from this triangle. We are also assuming that theta will be distributed uniformly due to the initial random spin, and it can take values from 0 to pi over 2. We don't need to consider the range from pi over 2 to pi, because that's symmetric to 0 to pi over 2 case. Now, remember that the uniform probability density function in general is given by 1 over b minus a. So for our case, it will be 1 over pi over 2. Now let's substitute x to our lambda theta. Next, we need to find the expected value of lambda theta using the uniform density. That's going to give us the probability that the needle crosses a vertical line. Let's call that p sub cv. Now we write it down as an integral since theta is continuous, substituting lambda theta and p theta and carrying out the integral should give us the answer. Next, let's move to the part B. Here we have horizontal lines in addition to the vertical lines on the table. And the question asks us the mean number of lines the needle crosses. Now, remember that in the previous part, one needle could have one crossing, as L is smaller than A. And we found the probability of the needle crossing a line, which is PCV. But we argue that this is the same thing as the mean number of vertical rulings crossed. Imagine throwing a very large number of needles on the table. Then the ratio of the number of needles that cross the lines to the number of total needles is the probability of needle crossing a line. Again, one needle can cross only one line in the previous case. So the PCV is the same thing as the mean number of vertical lines crossed. Now we argue that this probability is also equal to the probability of needles crossing a line if only horizontal lines existed. Let's call that P sub CH. These two are equal because if you rotate the table 90 degrees, you get the same problem. Also note that PCV and PCH are independent and disjoint events. Let's draw the grid to explain that. PCV and PCH are disjoint because one crossing can either be corresponding to a vertical crossing or a horizontal crossing, but not both at the same time. Don't confuse this with the needle being able to have both horizontal and vertical crossings. We are talking about one particular instance of a crossing. So the mean number of total crossings, let's call that M, is simply the sum of PCV and PCH, which in this case will be 4L divided by pi A. Now let's move on to the last part. So far we had L is smaller than A. In this part, the length L is arbitrary and we have both horizontal and vertical lines on the table. Let's call the length of these new large needles to be capital L. And again, we need to find the mean number of lines with large needle crosses. Call that capital M. Now, since we know the answer for small needles, where L is smaller than A, we are going to divide the large needles to n small needles. So the length of the smaller needles is going to be 2L is equal to capital L divided by n, which is again smaller than 2A. These smaller needles are going to cross m times on average, which we know from the previous part. Now we use the linearity of expectation, which tells us that the mean of sums is equal to the sum of means. So we can write capital M is the sum of small m's, which is equal to n times m. Substituting small m from the previous part and noting that 2L times n is the length of the larger needle, we get 2 capital L over pi A as the answer. Okay, so why is this problem important? Well, you have a geometric problem that is apparently consisting of just straight lines, but you get a pi appearing in the answers. And that's basically because you spin the needle, which gives a rotational aspect to the problem. Next, if you rearrange the above answer, you get an expression for pi, which you can compute using a sampling technique. So here capital L and A are known, and M will be the mean number of crosses calculated from throwing a large number of needles. And that gives us a very interesting and unique way of sampling the value of pi.